In this section, we're going to talk about how we can find the area under a graph. We're going to start by looking at what's called Reimann Sums. And what we can do is we can estimate the area under any graph by finding the area of some rectangles. So for this example, this would be a realistic real-life example. If a surveyor has to estimate the area of a waterfront lot, he's not going to have a formula for this lot. He's not going to have a formula for this water line here that's a nice curve. What he could do is he can measure the distance from the road to the river, and he could do this, say, every 20 feet. If he wanted to be more accurate, he could do it every 10 feet. So what he did is he chose, and he didn't have to, but he chose to come 10 feet in and measure, and that was 39 feet from the road to the river. And at 30 feet in, it was 46 feet from the road to the river. At 50 feet, it was 44 feet in, etc. And you can look at this and say, okay, he actually did 1, 2, 3, 4, 5 rectangles. So I'll erase those. And so these distances from the road to the water line are the heights of our rectangles. I could even redraw this, and it might make it easier without everything. So this one is 39 feet wide. The next one is 46 feet, 44, 40, and 41.5 feet long. So these are the heights of each rectangle. So what would be the widths? Okay, so notice each rectangle is 20 feet because he measured 20 feet. So from here to here, this rectangle is actually 20 feet, and from here to here is 20 feet. So our widths are, each one is 20 feet. So our widths are 20 feet, and there are 5 rectangles. He did 5 measurements. And we can estimate the area of this waterfront lot because area of a rectangle is length times width. And we can find the area of each rectangle and add them together. So my first length, I guess, would be 39 times 20. And my next one would be 46 times 20. And 44 times 20. Oh, oops, I forgot my plus. 44 times 20 plus 40 times 20 plus 41.5 times 20. And if I add all of those up, I'm going to get 4,210 square feet. And that would be my estimate of the area of the rectangle, or the area of the entire lot. Now obviously he's not going to be exactly correct because this is a curve, not a nice rectangle, so he's missing, or he estimated too much there, but he's missing some here. And he's off by a little bit here, and a little bit here, and a little bit here. So sometimes he's a little over, sometimes he's a little bit under, which is nice because those kind of cancel each other out a little bit. And what he could do is he could take even more rectangles, and then if we did even more rectangles, he'd be closer and closer to the actual curve. So we estimate this area. This is something that we do in applied situations where, again, you're not going to know the function of that water line, the function of that curve. But you can always estimate it with rectangles. This is also useful if you're a theoretical mathematician. What this means is we did the one estimate using Reimann Sums here, where we estimate the area with rectangles. We're not actually going to talk about this anymore in this class. If you look in the book, they talk about it a lot. Okay? But it takes a lot of time to do it by hand, and it's not something that you really need to do by hand. So we're not actually really going to do it again. This is just so you saw what it is. Oh, and just a little bit more theory. What would happen if you used more rectangles? So you can see, here's a theoretical curve. This is the true area under the curve. Here they did 2 rectangles, and you can see that they're off by quite a bit, right? So they're off here, here, and here. Like, that's all where they're going to be off. But if they do 4 rectangles, now they're not off by actually as much. They're a little bit closer. And if they do 10 rectangles, they're even closer. In fact, now here they're really quite close, right? If they did 20 rectangles, they would be even closer. So if you want to be more accurate, you do more rectangles. So more rectangles means that you are more accurate. Or you could also think about it, look at this, notice how the rectangles are getting skinnier and skinnier. Okay. So we come down here. If you use more and more rectangles, the rectangles get skinnier and skinnier. Now, because this is a calculus class and we know about limits, we can say as the width of the rectangles approaches 0, okay, or we could say the limit as the width approaches 0 of our rectangle estimate area, you're going to get closer and closer to the true area. So up above, again, when we went to 10 rectangles, our estimated area is going to be a lot closer to the true area. So as the width goes to 0, our estimate is going to equal our actual true area. And it turns out, again, this is calculus, so you shouldn't be surprised to realize that we can actually use an integral. So instead of estimating it with rectangles, which takes a long time, we can do the integral. If you know the function of that curve, you can just integrate it from a to b, that's your starting and ending point, a to b. Just take the integral and you will get the area. So that's very nice. So again, if you want to find the area, we just take the integral. So, and just to mention some technicalities, Reimann sums can become very technical, so if you actually studied the book and took a Calculus 1 class, you'd have to spend a lot of time with them. You talk about things like, should you measure the height of the rectangle at the top right corner, the top left corner, or the midpoint of the top edge, or you could use trapezoids, or you can use other rules that are made to make this more and more accurate. Again, you would only bother doing this in a really applied situation where you don't know the function of the curve, like when we talked about the water line for our lot. But in this class, we're just going to use integrals for functions that we do know what the function of the curve is. So we can find the area under the graph of our function f from a to b. So a to b is where you want to start and stop with this integral. So if this is your function f of x, here's a, this is where you want to start, here's b, this is where you want to stop. You can see how they shaded in the area you want to find. You just take the integral, and that's your area. So let's try an example. Let's find the area of the graph under the graph of y equals x squared minus 5x. So here's my curve from x equals 1 to x equals 4. So that's my a and b. That's where I want to start and stop. Let's write out. So I'm taking the integral of x squared minus 5x plus 10. dx, we always take an integral. We have to put our dx to tell us what we're differentiating. We're going to go from 1 to 4. At this point, now it just goes right back to what we did in the last section. It's not truly anything new. We're just taking the integral. So the integral of x squared, that would be x cubed divided by your new power, minus this 5x. That's like x to the power of 1. So this would be minus 5. Take the x, raise it by 1, and divide by your new power, plus 10. And if you remember, the integral of 10 would be 10x. And we need to evaluate this from x equals 1, sorry, you can't see that, to x equals 4. And we don't always put the x equals, it's always implied, but sometimes we don't write it once we get used to what we're doing. So let's plug in the 4 first. You plug in the top number first, so it's going to be 4 cubed over 3 minus 5 times 4 squared over 2 plus 10 times 4. So we do all of that minus, now we're going to do the exact same thing with my lower limit. So 1 cubed over 3 minus 5 times 1 squared over 2 plus 10 times 1, which gives me, it gives me 13.5. So that is this area right here under the curve from A to B. Now what if we wanted to break it up? So what if we have a piecewise function? So right here, from here to here, it's the function negative x plus 7. From here to here, it's the function x minus 3. And I want to find the area for all of this. So what would you have to do? You have to do two integrals. So we're going to do two integrals. We're going to do the integral of negative x plus 7. Okay. And we're going to do it from 0 to 5 because that's where that piece of the function is negative x plus 7. So we'll integrate from 0 to 5, then plus, and now we're going to do the integral for the second piece, and this one will go from 5 to 8. So the integral from 5 to 8 of x minus 3 dx. So let's do just one piece at a time. Let's take the integral from 0 to 5 of negative x plus 7 dx. Okay. So this is going to be negative x, raise it by 1, so from 1 to 2 is 2, divide by 2, plus 7x, and we need to evaluate from x equals 0 to 5, which is going to be, plug in the 5 first, so negative 5 squared over 2 plus 7 times 5. Minus, and now I do it with the 0, so negative 0 squared over 2 plus 7 times 0, which is going to be 22.5. Sorry, we're kind of running out of room here. Now let's do our second integral. So the integral from 5 to 8 of x minus 3 dx is going to be x squared over 2 minus 3x, evaluated from x equals 5 to 8, which is going to be 8 squared over 2 minus 3 times 8. And then minus, now we do the bottom limit, so 5 squared over 2 minus 3 times 5. Which is 10.5. And then my total area, we have to add those together. So 22.5 plus 10.5 equals 33. And just as a final technical note, when we talk about the area under the curve, we didn't actually say it, but if you come back up and look at our example, area under the curve, we didn't keep coming all the way down under the x-axis. We stopped at the x-axis. So for logical reasons, they said the area under the curve stops at the x-axis, or kind of stops at 0, because we kind of apply it to physical functions where usually your height starts at 0. And in our next section, we'll figure out how to do things if you don't actually want it to be between the x-axis and the function, if you want it to be between the x-axis or between the function and 1, or between two curves or something like that.